Welcome to Brain Vision.
For a RC circuit, the charge on the capacitor and the current in the resistor both decrease with time. Both decrease exponentially with time, with a time constant equal to R times C. So the time constant is RC that we already plugged over here. Now I naught is equal to V naught over R by Ohm's law. So we plug this over here. But before that, we also know that V naught is Q naught over C by Faraday's law. So we combine these two equations and we get I naught to be equal to Q naught over RC, and then we plug this expression of I naught over here to get the current, which comes out to be equal to Q naught over RC times e to the power minus t over RC. Now the energy stored in the capacitor is given by half Q square over C, and the power, let me just decrease the size a little bit. So this is the potential energy, and the power dissipated in the resistor is given by I square times R. So we will use that later in this problem. First, let's find the decrease in energy. So you decrease, okay, let me just move this expression to here, or maybe here, to save some pages. Okay, now let's find the decrease in potential energy. So this will be equal to, so if del U is the change, negative del U is the decrease in potential energy. So here we have t equal to 0 and then t equal to tau for both the initial and final. Now let's plug this expression over here. So at t equals to 0, we have Q equal to Q naught, because e to the power 0 is just 1. So for the potential energy at t equals to 0, we have Q naught square over 2C. And at t equals to tau, and tau being RC, e to the power minus tau over RC becomes just e to the power minus 1. So Q is Q naught over E. So for this case, we have Q naught e to the power minus 1. I have to take a square because the charge square over 2C. So from here we get the decrease in potential energy to be equal to, so one more thing that you might find confusing is, remember that the decrease in potential energy is negative of the change in potential energy, and the change in potential energy is in fact the final minus initial, which is U at t equal to tau minus U at t equals to 0. So U at t equal to tau is the final potential energy, and U at t equals to 0 is the initial potential energy, just like the common case. But since there is a negative sign here, the del U gets, the signs gets change, and finally we have ut equals to 0 minus ut equals to tau. So that's what we did. Now let's simplify this expression a little bit. So we take q naught square common out of these two terms, and also we take 2c common out of these two terms, and we are left with 1 minus e to the power minus 2. So this is the decrease in potential energy. Now let's find the dissipated potential energy. So before that, let me just change the size of this a little bit. Oops. So we can have some more space. Now let me just move this to here. Okay. Now U dissipated. Oops. I think just this is fine. So we know that power is the rate of change of energy. So power is the rate of change of energy, potential energy. So the dissipated energy, the total energy dissipated, will be integral over power with time. Now let's use this expression of power over here. So we have I square R dt, and we are going from 0 to tau. Oops, I think there is, yeah, 2c was missing, so I wrote that. Now we are going from t equals to 0 to t equal to tau. So those are our limits. And the general expression of I is over here, that we will be using in this integral. So that will be equal to q naught over rc e to the power minus t over rc. So we have to take a square, and then there is resistance R and integral over dt. Now let's take the constants out of the integral. So q naught square over rc square. So this is a constant term, and let's keep the time dependent terms inside the integral. So this is our simplified equation. Now we do the integral for this. So we know that this integral will be minus rc over 2 times e to the power minus 2t over rc. I'll write the formula after a while. I'll write the formula for this in a while. So let me just solve this quickly. So we put the limits now, and we simplify this expression after putting the limits. So as you can see, the r and r here cancel out, and there is an extra c that should be here. So it's just q square over c. However, there is a 2 in the denominator, so let's write that. And after putting the limits, we get e to be equal to 1 minus e to the power minus 2. So we get this to be equal to 1 minus e to the power minus 2 after putting the limits and taking this negative sign into account. Now about the integration here. So if your integral is of this form, let's keep it indefinite for now. So this integral will be equal to e to the power minus x over x. And in this case, your x is, oops, I missed a t. Yeah. And in this case, your x is 2 over RC. So 1 over x will be RC over 2. So that's what we did. And if your limits are a to b, so you just do the integral and then put the limits. So this will be equal to e to the power minus xb minus e to the power minus xa over x. So that's what we did after putting the limits. Now, if you compare the decrease in potential energy and the dissipated potential energy, which is this boxed equation here, you'll see that these two are equal. So this means that U decrease is equal to U dissipated. And this is what we were supposed to show for the problem, and we proved that.